Okay, section 6. So we're getting close to the end of chapter 1, roots and radicals. And we're going to look at how these play out, and how we work with these radical ideas. A square root. So this is the most common one that most people are familiar with. Is a square root. And if x is some non-negative real number, and we'll talk about what a not real number would be in the next chapter, or the next section. The square root of x is called the positive square root. So this symbol here is called the positive square root of x, such that if you squared it, if you did the square root of x times the square root of x, the square root of x squared, you would get that number x back out again. So as an example, the square root of 9. The square root of 9, when you see that symbol, this notation, they want the positive result. They want to know that the answer is 3. 3 times 3 is 9, and so the square root of 9 is going to be 3. If you took the square root of 9 and then you squared it, you would get 9 again. That's the idea. There you go. It does work for other roots as well, not just square roots. Cubed roots, so a little 3 here means that we're taking a cubed root. We're wondering something times itself 3 times gives us 125. 5 times 5 times 5 equals 125. And so the cubed root of 125 is 5. The only root that does not get a special number, like this 3 for cubed root, is a square root. So we are assuming that a square root is 2, because the square root of x squared is x. The cubed root of x cubed is x. There it is right there. 5 to the third power is 125. And so square root does not get a number, but we assume it's a 2. And anything other than that gets its own special number. So that's how that notation plays out. Negative roots. The square root of negative 16 is a strange one because the most obvious answer would be negative 4. However, negative 4 times negative 4 is not negative 16. Negative 4 times negative 4 is a positive 16. So negative 4 is out. Positive 4 doesn't work either, because 4 times 4 is a positive 16. So positive 4 doesn't work, negative 4 doesn't work, and it has to be times itself. So it can't be negative 4 times positive 4. Those are two different numbers. So there is no real number. There is a number. There is an answer to this. It's just not a real number. And so when you see that, the answer is not real. It's not that it doesn't exist. That's not true. It does exist. It's just that it's not a real solution. And in the next section, we'll talk about what it means to not be a real solution and still be a solution. But for now, for this section, it's not real. The cubed root of negative 8, this does have an answer. So just because it's a negative inside of that radical sign, these root symbols here are called radicals. Just because there's a negative inside does not mean that there's no real solution. Negative 2 times negative 2 times negative 2 is negative 8. So the cubed root of negative 8 is negative 2. We do get a solution. It's a real solution. The only times you really have to be careful, well, all the time you have to be careful, but the only time that it causes an issue is when you have an even radical. So square root or quartic root, that'd be a 4, 4th root, 6th root, 8th root, so on. Any root that's an even root, you cannot get a real result from that negative number. If it's an odd number, like the third cube root, a third root, or a 5th root of a negative number, that's okay. That works just fine. Properties of exponents. We've already gone through most of these. We've gone through 4 out of 6 of these. So in section 2, I believe, the very first video, we went through 3 of these already. So I'm not going to spend a lot of time on all of them. The first one we already talked about. If you're multiplying 2 powers, you can add the exponents together. The second one we already talked about. If you have a power raised to another exponent, you can multiply those exponents together. That's the shortcut. Number 6 we already talked about. If you divide, the quotient rule, if you divide 2 powers, you can subtract the exponents. And number 4 we talked about, where if it's a negative exponent, it becomes a fraction. So a to the negative r is the same as 1 over a to the positive r. And that's how we deal with those negative exponents. The two that we have not talked about are number 3 and number 5. And these ones are intuitively make some sense. And we're not going to go into a lot of depth into why and how, but intuitively they do make sense. If you have two numbers being multiplied together, a times b, to the sum power, so their product is being raised to the r power, we can essentially, it's not really distributing, but we can essentially distribute this r through the parentheses. And it becomes a to the r power and b to the r power. Now I'm saying distribute it very loosely. That's what appears to be going on. And effectually that is what happens. But there's a lot more to it. We're just not going to worry about it. Same thing with division. If you have a fraction, a divided by b, we can distribute that r through the parentheses. And again, I'm being very loose with that word distribute in this case, but it becomes the same as a to the r and b to the r. So we can basically break up the parentheses and use that exponent in each separate piece. One thing I do want to point out, this only works for multiplication and division. It does not work for addition. So if it's a plus b to the r, remember at one point there was a slide with Batman slapping Robin. Don't do that. You can't distribute through if there's a plus r, then we have to do FOIL. We have to expand those out. So only works for multiplying and dividing, but it's a nice slick property to use. Okay, radical exponents, which is kind of a weird thing to say all on its own. Radical exponents. What we're looking at in this section or in this part of the unit is rewriting things. It's kind of like you could write 1.5 as 3/2. You could write it as a mixed number or an improper fraction. There's two ways of writing the same meaning. That's what we have here. If you have an nth root, let's say a third root, cubed root of x, a different way of writing that is x to the 1/3. That's it. It's just a different way of writing a radical. So if we have the fourth root, so there's a fourth root of 16 x to the 8th, y to the 4th. A different way of writing this, if we wanted to try and simplify this down a little bit, a different way of writing that radical sign, that fourth root here, is to change that fourth root into an exponent that's a fraction. Since it's a fourth root, it becomes an exponent of 1/4. So again, we're not doing anything with the 4. We're not multiplying, dividing. We're not doing it. We're just rewriting it in a different way. And the benefit of that is we can use this new exponent property that says if all these are being multiplied together, we can bring that 1/4 through to everything inside those parentheses. So I'm going to kind of do this the longhand. I'm not going to take any shortcuts. I'm going to bring that 1/4 through to everything inside the parentheses. So it'd be 1/4 times 4, 4/4. 1/4 times 8, 8/4. 1/4 times 16, well, not 16, just 1/4 times, I guess, 1, so 1/4. Now the 16 to the 1/4, this part right here, this is a little bit trickier. This is where you would maybe want to use a calculator, unless you can see it right away. We're asking something times itself 4 times, because it's a fourth root, something times itself 4 times gives us 16. Happens to be that 2 times 2 times 2 times 2 is 16. And this is, again, where you could use a calculator and just type that into your calculator and say, well, what is 16 to the 1/4 power? And it would give you the answer of 2. With the variables, it works a lot nicer because we have this fraction, but this can be reduced. 8/4, 8 divided by 4, is the same as 2. 4/4, 4 divided by 4, is the same as 1. So this original expression here, the fourth root of 16 x to the 8th power, y to the 4th power, by using this new notation that we have with a fraction as an exponent, we were capable of using some exponent properties, stuff we already have some familiarity with, and simplify it down to just this. So we took something that was fairly complicated and made it a lot easier to work with. 2x squared y. So it's a method, it can be used as a method of simplifying things down. And we'll get some practice with that. One thing I'm going to mention with it is if you have okay, so let's say we have an exponent of 2/3. So again, with that last one, we had 8/4. 8/4 is really the same as 2. 8 divided by 4 is 2. Here we have 2/3. There's two ways of reorganizing this or rearranging it, and neither one is better or worse. It kind of depends on you and what you're familiar with. One way to rearrange this is, I guess I have both. One way to rearrange this is to say, well, it's a third, 2/3, so that 1/3 power I could bring out here. I could split this 2/3 up into 2 times 1/3. Or I could split it up into 1/3 times 2. 2 times 1/3 is 2/3. 1/3 times 2 is 2/3. So it's the same thing. And you might be wondering, well, why even bother to talk about it? The only benefit here is if you weren't going to use a calculator, if you were going to try and speed up the process and not use a calculator, I have no idea what 27 squared is. It's just not something I have in my memory bank. However, 27 to the 1/3 power is the cubed root of 27. So something times itself 3 times, cubed root, is 27. I happen to know, just because I do a lot of math problems, that 3 times 3 times 3 is 27. So I could jump, in this one here, I could jump straight from the cubed root of 27 to just 3. I could not have done this 27 squared in my head. However, since most of you are probably going to use a calculator for many of these problems anyways, it doesn't really matter. You could do 27 squared in your calculator and get 729. Back over here on the right, I can do this very easily in my head. 3 squared is 9. So the answer, 27 to the 2/3, is 9. And I could have gotten that from 27 to the 1/3 is 3, squared is 9. You could have done it this way and say, well, 729 to the 1/3 power is 9. I mentioned that simply because recognizing perfect squares and recognizing perfect cubes speeds up the process. You don't need a calculator as much, but it's not necessary. Okay, two little properties here that work just like the exponents because, again, radicals are exponents. So when we talked about the exponents and said, well, you could just distribute the exponent through. Same thing with radicals. The square root or the nth root of a times b is the same as the square root of a times the square root of b. We can split this multiplication up into 2 roots. So we're able to combine roots together. The square root of a times the square root of b is the same as the square root of a times b. Same thing with division. The square root of, and I say square, it could be any root. The square root of a divided by b, we can split that up into the square root of a divided by the square root of b. We can separate those out, separate that fraction, or we could put them back together again. So if we have the square root of a divided by the square root of b, we can put them back inside of one square root. So these two properties just allow us to split up square roots that are being multiplied or divided, or put them back together into one radical. And again, this only works for multiplying and dividing, not adding and subtracting. Okay, I'm going to go a little bit further. I take that back. Before I stop and go a little bit further, I'm going to come back to this. I'll come back to this here in a little bit, but simplified form. You can pause it, read it on your own. I'm gonna do examples that'll kind of identify what we're looking at. Rationalizing the radical, factor trees. There are 2 ways to rationalize a radical. This is like reducing a fraction. 3/6 is the same as 1/2. So reducing a fraction, that's kind of what we're doing here, rationalizing the radical. And this does have some different uses. So we're going to talk about it. What the text would have you do, what the textbook says, this is how you should do it, is to look at 18 and be able to know or identify what are the factors of 18. So factors being like 2 times 9, 3 times 6, 1 times 18. And knowing all the different factors of 18, are any of them perfect squares? Because this is a square root, we're looking for perfect squares. Are any of the factors of 18 perfect squares? And they would have you, just by looking at it, say, well, 9 is a factor of 18. 9 is a perfect square. So we could rewrite this as 2 times 3 squared. That seems like a lot for you to just know, to just look at it and go, oh yeah, obviously, 18 has a factor that's 2 times 9, 9 is a perfect square. But that's what the text has you do. I'm going to show you a different way here in a minute. The benefit or the use of this, once you get to this point, and I'll show you how to get to this point in a different way here in a minute. But the usefulness, boy, you know what? I'm going to show you how to get to that point first. So I'm going to get out of that for a minute and go to my document camera. So we're looking at 18. And you can't really read that. So let me, come on, camera. There we go. Okay, let's try that again. All right, so we're looking at 18. All right, that's better. If we want to find that 2 times 3 squared is really what came out of it. Another way to do it besides just knowing it is to do a factor tree. So a factor tree, if you haven't done these before, is you're coming up with the factors. So I could say 3 times 6 is 18. And I'm looking for prime numbers. It's called prime factorization. 3 is prime. 6 is not prime. A prime number means that the only factors are 1 and itself. So I'm trying to find 2 factors of 6. I know that 2 times, so I'm going to go 3 times 2 is 6. Again, 3 is prime. There's no numbers that multiply to 3. There's no numbers that multiply to 2 besides itself and 1. So I have the prime factors. Because I'm doing the square root of 18, which is like a 2, even though we don't write the 2 there, it's a square root, so it's 2. I'm looking for groups of 2. There's 2 3s here. That means that I'm doing the square root of 3 squared times 2, which is what we had in the last slide. I'm going to continue here. The square root of 3 squared, we showed this at the beginning, that the square root of x squared equals x. That was the beginning slide. So the square root of 3 squared is 3. The square root of 2 is some crazy decimal. So I'm going to leave it as the square root of 2. Essentially what we're doing is we're looking for a group of 2. We've got 2 3s. We're basically pulling that 3 out and leaving whatever's left over inside the radical. And that's what we see if I go back into my presentation mode here, right here. That's the longhand way of doing it, but we get the same result. Let's do another one. Square root of 48. Square root of 48. So I'm going to go back to my document camera, and I'm going to do a factor tree for 48. So I'm trying to find the square root of 48. I need 2 factors of 48. 6 times 8 is 48. Neither of those are prime. 3 times 2 is 6. 2 times 4 is 8. And 2 times 2 is 4. So I have my prime factors. I've made a prime factorization. Looking for groups of 2. I've got 2 2s. I've got another 2 2s. Because this is a square root, I'm looking for groups of 2. Because I have at least one group of 2 2s, I can bring that 2 outside of the square root. I've got another group of 2 2s. So I'm going to bring that outside the square root. And there's a 3 left over. So I'd have 2 times 2 times the square root of 3. And again, you could do it the long way, kind of like I did over here, and see that this is 2 squared and the square root of 2 squared and all that. But this is the kind of the faster way of getting to that same answer, which means our final answer, 2 times 2 is 4 root 3. And that would be the final simplified, rationalized radical. Again, there's that longer way of writing it to get the answer of 4 root 3. Okay, I'm going to pause. I think I've made the video a little bit too long as it is. I'm going to come back and we'll finish up in a second video.